When determining the appropriate wire size for feeding a 200 amp subpanel, you can generally reference the same wire chart that you used for sizing the service entrance conductors. For a 200 amp subpanel using aluminum conductors, a typical wire size would be 4/0-4/0-2/0 aluminum. If you're using copper conductors, a common choice is 2/0 copper. The reason you can use the same wire chart is that the subpanel is located downstream from the main service entrance. This means that the subpanel will never be subjected to a higher current than what the service entrance is rated for. By using the same wire chart, you ensure that the conductors feeding the subpanel are adequately sized to handle the expected current load from the main panel. However, there are other factors to consider. Firstly, the subpanel itself must be rated for 200 amps to accommodate the full current capacity of the conductors you're installing. Secondly, it is essential to ensure that the conductors are properly terminated and securely fastened within the subpanel. This is crucial for maintaining safety and ensuring the long-term reliability of the electrical connection. Remember that electrical codes and regulations may vary depending on your location. Always consult your local electrical codes or a qualified electrician for guidance to ensure compliance with all applicable requirements. Choosing the correct wire size is crucial for safety and proper function. Undersized wires can overheat, potentially causing fires. Overly large wires, while safer, are more expensive and can be difficult to work with. The National Electrical Code, or NEC, provides guidelines for wire sizing based on ampacity, which is the current carrying capacity of a conductor. Several factors influence ampacity, including the wire material, its insulation type, and the ambient temperature. Aluminum and copper are the most common conductor materials. Copper has a higher conductivity than aluminum, meaning it can carry more current for a given size. However, aluminum is lighter and less expensive, making it a popular choice for larger conductors. Insulation type also affects ampacity. Different insulation materials are rated for different maximum operating temperatures. Higher temperature ratings allow for higher ampacities. The NEC provides tables that list the ampacities of different wire sizes and insulation types at specific temperatures. Ambient temperature also plays a role. The ampacity of a conductor decreases as the ambient temperature increases. This is because higher temperatures increase the resistance of the conductor, which leads to more heat generation. The NEC provides correction factors to adjust ampacity based on ambient temperature. When sizing wires, it's important to consider the load they will be carrying. The load is the amount of current that the connected devices or appliances will draw. The wire must be able to handle the continuous load, which is the maximum current expected to flow for 3 hours or more. The NEC requires that conductors be sized to carry at least 125% of the continuous load. This provides a safety margin to prevent overheating. In addition to the continuous load, it's also important to consider any non-continuous loads. These are loads that are only expected to operate for short periods of time. The wire must also be able to handle the sum of the continuous and non-continuous loads. Voltage drop is another important factor to consider when sizing wires. Voltage drop is the decrease in voltage that occurs along the length of a conductor. Excessive voltage drop can cause appliances to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. The amount of voltage drop depends on the wire size, the current flowing through the wire, and the length of the wire. Larger wires have low resistance, which results in less voltage drop. Shorter wires also have less voltage drop. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times the length of the conductor in feet times the current in amps times the impedance of the conductor in ohms per foot, divided by 1000. The impedance of the conductor depends on the wire size and material. The NEC provides tables that list the impedance of different wire sizes and materials. In addition to the NEC, local electrical codes may also have requirements for wire sizing. It's important to check with your local electrical inspector to ensure that you are following all applicable codes. When installing wires, it's important to follow proper wiring practices. This includes using the correct connectors, making secure connections, and protecting the wires from damage. Improper wiring can lead to electrical hazards, such as shocks and fires. Wires should be protected from physical damage by using conduit or other protective measures. Conduit is a metal or plastic tube that is used to enclose and protect wires. Wires should also be supported properly to prevent them from sagging or straining the connections. When making connections, it's important to use the correct type of connector for the wire size and material. The connectors should be properly tightened to ensure a secure connection. Loose connections can cause overheating and arcing. Grounding is an important safety measure that helps to protect against electric shock. Grounding provides a low resistance path for fault current to flow back to the source. This allows the circuit breaker or fuse to trip, cutting off the power and preventing a shock. All electrical equipment should be properly grounded. Grounding conductors should be sized according to the NEC. In addition to grounding, it's also important to use ground fault circuit interrupters, or GFCIs, in areas where there is a risk of electric shock, such as bathrooms and kitchens. GFCIs are devices that monitor the current flowing through a circuit and trip if they detect a ground fault. A ground fault is a situation where current is flowing through an unintended path to ground, such as through a person's body. GFCIs can help to prevent electric shock by quickly cutting off the power in the event of a ground fault. Surge protection is another important safety measure that can help to protect electrical equipment from damage caused by power surges. Power surges are sudden increases in voltage that can damage sensitive electronic equipment. Surge protectors are devices that divert excess voltage away from the equipment and into the ground. Surge protectors should be installed at the service entrance and at individual outlets where sensitive electronic equipment is connected. Regular electrical inspections can help to identify potential problems and prevent electrical hazards. Electrical inspections should be performed by a qualified electrician. The electrician will check the wiring, grounding, and other electrical components to ensure that they are in good condition and comply with electrical codes. If any problems are found, the electrician can recommend repairs or upgrades. Electrical safety is everyone's responsibility. By following safe electrical practices, you can help to protect yourself and your family from electrical hazards. If you are not comfortable working with electricity, it's best to hire a qualified electrician. An electrician has the training and experience to safely and properly install and repair electrical systems. Remember that working with electricity can be dangerous. Always take precautions to protect yourself from electric shock. Wear rubber gloves and shoes and avoid working in wet conditions. Turn off the power before working on any electrical circuit. If you are not sure how to do something, ask an electrician for help. Here's a slightly more detailed breakdown of calculating wire size using the NEC. Firstly, determine the ampacity needed. This is the maximum current the wire needs to carry. For a 200 amp subpanel, you'll need a wire with an ampacity of at least 200 amps. Secondly, consider the conductor material. Copper and aluminum are the most common choices. Copper is a better conductor but is more expensive. Aluminum is light and less expensive but requires larger sizes for the same ampacity. Thirdly, choose the insulation type. Common insulation types include THHN, THWN, and XHHW. Each type has different temperature ratings, which affect the ampacity. Fourthly, check the NEC ampacity tables. Table 310.15. B16 in the NEC provides ampacities for various wire sizes, insulation types, and temperature ratings. Fifthly, apply correction and adjustment factors. If the ambient temperature is higher than 30 degrees Celsius, 86 degrees Fahrenheit, or if there are more than 3 current-carrying conductors in a raceway, you'll need to apply correction and adjustment factors to the ampacity. Sixthly, calculate voltage drop. Use a voltage drop calculator or the formula mentioned earlier to ensure the voltage drop is within acceptable limits, typically 3% for branch circuits and 5% for feeders. Seventhly, select the appropriate wire size. Based on the adjusted ampacity and voltage drop calculations, choose the wire size that meets or exceeds the requirements. Eighthly, ground wire sizing. The grounding conductor should be sized according to NEC Table 250.122, based on the size of the ungrounded conductors. Finally, conduit sizing. Ensure the conduit is large enough to accommodate all the wires being installed following NEC Chapter 9 Table 1 guidelines. Here is an example of wire size calculation for a 200 amp subpanel. Let's assume we are using copper conductors with THHN insulation in an ambient temperature of 30 degrees Celsius and there are no more than 3 current carrying conductors in a raceway. Step 1. Determine the ampacity needed, 200 amps. Step 2. Choose copper conductors with THHN insulation. Step 3. Check NEC Table 310.15. The 16. According to this table, a 2/0 copper wire with THHN insulation has an ampacity of 175 amps at 75 degrees Celsius, while a 3/0 copper wire has an ampacity of 200 amps. Step 4. Apply correction and adjustment factors. Since the ambient temperature is 30 degrees Celsius and there are no more than 3 current carrying conductors, no correction or adjustment factors are needed. Step 5. Calculate voltage drop. This calculation depends on the length of the wire run. Let's assume a wire run of 100 feet. Using a voltage drop calculator, we find that a 3/0 copper wire will have a voltage drop of approximately 2.2 volts at 200 amps, which is within the acceptable limit of 3% for branch circuits, which would be 7.2 volts on a 240 volt system. Step 6. Select the appropriate wire size. Based on the ampacity and voltage drop calculations, a 3/0 copper wire is the appropriate size for this application. In summary, for a 200 amp subpanel using copper conductors with THHN insulation, a 3/0 copper wire would be a suitable choice. However, always consult the latest NEC guidelines and local electrical codes, and it is highly recommended to consult with a qualified electrician to ensure compliance and safety. Also, remember to size the ground wire and conduit appropriately based on the selected wire size.